Section: Introduction. In this section, we discuss the significance of large language models, LLMs, in natural language processing and the challenges they face, such as generating misleading information. Uncertainty estimation has become crucial to assess the confidence levels of LLM outputs. While uncertainty estimation has advanced in machine learning and deep learning, it lags behind in LLMs due to the variable nature of natural language generation tasks. Existing uncertainty estimation methods for LLMs focus on designing metrics based on output characteristics like consistency and entropy. White box LLMs, providing access to inner values like logits and hidden layers, are believed to offer better uncertainty estimation. Supervised approaches are gaining traction in LLM uncertainty estimation to leverage both outputs and internal states for improved reliability. Our study evaluates incorporating hidden states of LLMs in supervised uncertainty estimation to enhance confidence and reliability. We define the uncertainty estimation problem for LLMs, highlighting differences from traditional ML models. We propose a supervised method mapping hidden activations and probability information to uncertainty scores, applicable to various LLM types. Experimental results across NLP tasks show our approach consistently improves uncertainty estimation by extracting additional knowledge from LLMs. Section Summary. In this section, we delve into the challenges faced by large language models, LLMs, due to their tendency to generate misleading information, leading to the emergence of uncertainty estimation as a crucial problem. We explore the differences in uncertainty estimation for LLMs compared to traditional machine learning models, emphasizing the need for supervised approaches that leverage hidden states within LLMs for improved uncertainty estimation. Our study proposes a supervised method that maps hidden activations and probability-related information of LLMs to uncertainty scores, demonstrating enhanced uncertainty estimation across various NLP tasks and shedding light on the method's robustness and transferability. Section: Related literature. In this section, we explore related literature on uncertainty estimation for natural language generalization. The uncertainty estimation and calibration for traditional machine learning have been extensively studied. However, with the rise of large language models, LLMs, there is a growing need to comprehend uncertainty in LLM responses. Measuring uncertainty from sentences, rather than fixed dimension outputs, poses a greater challenge. Some research focuses on unsupervised methods that use entropy, similarity, semantic, logit, or hidden states information to create uncertainty metrics for quantifying uncertainty in LLMs. For black box models, certain metrics can be computed based on multiple sampled outputs of the LLMs. On the other hand, white box models provide more information such as the output's distribution, logit values, and hidden layers, making it easier to compute the uncertainty metric. Other related methods for uncertainty estimation include calibration and conformal prediction. Recently, uncertainty estimation approaches have been applied to hallucination detection. By analyzing the values of logits and hidden states in LLMs, researchers aim to understand the trustworthiness of the generated output. Utilizing hidden layers activations, a classifier can be trained to detect hallucinations and develop neural networks to reduce them. The information from LLM's hidden layers can offer insights into the reliability of input queries, indirectly aiding in detecting hallucinations. Exploring hidden states within LLMs helps in understanding their behavior better. Researchers have used LLM's hidden states to train calibrators predicting output correctness likelihood. By leveraging hidden activations in language models, knowledge about the trustworthiness of outputs can be represented. It has been observed that LLM's outputs and internal states may provide conflicting information about truthfulness, and the reliability of outputs versus internal states varies across scenarios. In the problem setup, we interact with LLMs through prompts and responses. An LLM receives an input prompt and generates a response following a probability distribution based on its parameters. The evaluation function assesses the quality of the response, comparing it to the true response for the prompt. The task of uncertainty estimation for LLMs involves learning a function that predicts the evaluation score, considering the randomness of the true response. This function does not require the true response as input, broadening its applicability across different settings. The uncertainty score function aims to guide users on how much they should trust the response. It is defined on an individual level, ensuring precision in predicting scores for each prompt response pair. This calibrated score helps users gauge the reliability of LLM responses. In the upcoming sections, we will outline our method as a generic framework for uncertainty estimation, discuss its integration with state-of-the-art LLMs, present empirical findings, and explore its connection to existing literature on fine-tuning LLMs and hallucination detection. Section Summary. In this section, we explore uncertainty estimation for natural language generalization, particularly focusing on leveraging hidden activations in large language models, LLMs, for tasks like hallucination detection. By analyzing the hidden states of LLMs, we aim to predict the trustworthiness of their outputs and differentiate between true and false responses. Our approach involves training a calibrator using hidden activations to enhance the truthfulness of LLMs during inference, ultimately improving the reliability of their generated responses. Section: Uncertainty estimation via supervised calibration. In this section, we introduce our method of supervised calibration as a post hoc procedure to estimate the uncertainty of the LLM's responses. We adopt a supervised approach to learn the uncertainty function g, x, times y, right arrow, 0, 1, similar to uncertainty quantification for ML, deep learning models. Initially, we work with a dataset of n samples d underscore, text, raw, equals, x underscore I, y underscore I, text, true, s, y underscore I, text, true, underscore I equals 1, caret n. Here, d underscore, text, raw, is created based on a labeled dataset for the tasks we are focusing on. Each sample consists of a prompt x underscore I and the corresponding LLM's response y underscore I, where y underscore I, text, true, represents the true response for x underscore I, and s, y underscore I, text, true, assigns a score to the response y underscore I based on the true answer y underscore I, text, true. When generating the dataset d underscore, text, raw, with the LLM, there can be multiple samples with the same prompt due to tasks like question answering and machine translation. Even though these samples share the same prompt x underscore I, they may have different responses y underscore I because of the LLM's probabilistic nature. However, all these samples have the same true response y underscore I, text, true. Each distinct response y underscore I forms a meaningful sample for the uncertainty estimation task. Next, we create a supervised learning task using the dataset d underscore, text, raw. We form a new dataset d underscore, text, un, equals, v underscore I, z underscore I equals 1, caret n, where z underscore I equals s, y underscore I, text, true, in 0, 1, is the target score to predict. The vector v underscore I contains relevant features for the ith sample based on x underscore I, y underscore I, for the prediction task. This supervised learning task aligns with the definition of the uncertainty estimation task. We determine the feature vector v underscore I based on x underscore I, y underscore I, by considering features from two sources. Firstly, white box features involve the LLM's hidden layer activations. We input x underscore I, y underscore I, into the LLM and extract the activations of the hidden layers, focusing on the last token's activation as it contains crucial information. Secondly, gray box features include entropy or probability-related outputs. The entropy of a discrete distribution over the vocabulary is considered as a feature. We also explore other features such as the LLM's certainty about its response. Our goal is to train a model, hat, G, V_I, that predicts Z_I. By learning from the dataset D_text, we can develop a model, hat, G, that predicts the uncertainty Z_I using summarized features V_I. This supervised approach outperforms ad hoc methods like entropy-based or similarity-based methods, as confirmed by numerical experiments. This emphasizes the effectiveness of supervised learning in predicting uncertainty, aligning more with traditional uncertainty quantification methods. We aim to investigate whether hidden layers contain information about uncertainty, which is not commonly explored in existing uncertainty estimation literature for ML models. This distinction underscores the difference between uncertainty estimation for conventional deep learning models and LLMs. Through theoretical insights and empirical experiments, we demonstrate how the supervised approach can enhance uncertainty estimation by extracting additional knowledge from LLMs. Section Summary. In this section, we introduce a method called Supervised Calibration to estimate uncertainty in language models, LLMs. We create a dataset, D_text, raw, with samples of prompts and LLM responses, then formulate a supervised learning task using this dataset to predict target scores for uncertainty estimation. By leveraging features from LLM hidden layer activations and entropy-related outputs, we train an uncertainty model that outperforms traditional methods, shedding light on how internal LLM states encode uncertainty, a novel approach in the field. Section: Uncertainty Estimation versus Uncertainty Calibration. In this section, we have been focusing on two main tasks: uncertainty estimation and uncertainty calibration. Uncertainty estimation involves predicting whether the LLM makes errors in its responses, while uncertainty calibration ensures that the uncertainty estimation model conveys probabilistic meaning accurately. Our focus has been on improving the predictability of the LLM's uncertainty, leveraging our supervised formulation and the LLM's hidden activations for this purpose. We have observed that a better uncertainty estimation leads to a better calibrated uncertainty model, as confirmed by our numerical experiments. Moving on to why hidden layers are valuable as features for uncertainty estimation, let's consider a binary classification task with features and labels drawn from a distribution. We aim to learn a model that predicts labels from features using a loss function. Under the cross-entropy loss, the function that minimizes the loss coincides with the Bayes optimal classifier. This highlights the importance of having a rich function class and training on a large dataset. The conditional independence between the label and features under the Bayes optimal classifier sheds light on why traditional uncertainty quantification methods do not heavily involve original features or hidden layer activations. For LLMs, additional procedures are needed due to the lack of conditional independence. When the loss function does not align with the cross-entropy loss, the conditional independence collapses, emphasizing the difference in uncertainty estimation between traditional ML models and LLMs. In summary, uncertainty estimation for LLMs faces challenges due to the misalignment between model pre-training and uncertainty quantification tasks, leading to the collapse of conditional independence. This justifies our approach of using hidden layer activations as features for predicting uncertainty scores and explains the deviation from mainstream uncertainty quantification practices. Section Summary. In this section, we focus on the distinction between uncertainty estimation and uncertainty calibration tasks. While uncertainty estimation predicts errors in a language model, LLM, response, uncertainty calibration ensures that the uncertainty model conveys probabilistic meaning. By leveraging supervised formulation and LLM's hidden activations, we enhance predictability of LLM's uncertainty. Additionally, we explain why hidden activations are valuable for uncertainty estimation by highlighting the importance of features in capturing information about the uncertainty score, especially in the context of LLMs. Section: 3 regimes of supervised uncertainty estimation. In this section, we will explain the 3 different ways we can estimate uncertainty in a supervised manner. We assume that we know all the parameters of the LLMs, including the hidden activation and output probabilities. We divide our method into 3 categories to handle situations where the LLM is a black box and we don't have access to the parameter details. Our supervised learning method involves using an LLM to produce a response y for a given input x, and then analyzing the confidence level based on the hidden layers activations of the same LLM. This works well with white box LLMs where we can access hidden activations. However, with black box LLMs that limit access to hidden activations, we need alternative methods to estimate uncertainty. We realize that we can obtain hidden layers activations using any LLM and the input-output pair, x, y. This means that x, y doesn't have to be generated by the same LLM that provides the hidden activations. While it may seem logical to assume that the LLM generating x, y has more uncertainty information about y, any white box LLM can give hidden activations for x, y. We introduce our supervised uncertainty calibration method for white box, gray box, and black box LLMs. White box supervised uncertainty estimation, WBS, involves constructing features from 2 sources and training a model to predict uncertainty. Gray box supervised uncertainty estimation, G-flat-S, uses features only from the gray box source, focusing on probability and entropy. Black box supervised uncertainty estimation, B-flat-S, doesn't require knowledge of the parameters of the LLM P_theta, but aims to estimate its uncertainty using another open source LLM Q_theta. The original data, D_text raw, is generated by P_theta, but uncertainty estimation data, D_text un, is based on Q_theta. We use Q_theta, along with the uncertainty model from D_text un, to estimate uncertainty for responses from P_theta. Our algorithm summarizes the supervised approach for uncertainty estimation, considering scenarios where the target LLM is the same as Q_theta, white box and gray box, or different, black box. Section Summary. In this section, we introduce a method for supervised uncertainty estimation assuming knowledge of the parameters of the LLMs, categorizing it into 3 regimes to address scenarios where the LLM is black box. By utilizing hidden activations from LLMs, we can effectively estimate uncertainty, with white box LLMs providing direct access to hidden layers, while black box LLMs require alternative methods. Our supervised uncertainty calibration method is presented for white box, gray box, and black box LLMs, each involving different approaches to extract features and predict uncertainty in LLM responses. Section: Numerical experiments and findings. In this section, we systematically evaluate our supervised approach for estimating the uncertainty of the language models, LLMs. We provide details of the numerical experiments we conducted. The code used in our experiments can be found at the provided link. We mainly focus on 2 open-source LLMs, Llama 2-7b and Gemma 7b, as defined in section. Additionally, we sometimes use Llama 2-13b and Gemma 2b for specific experiments. We utilize their respective tokenizers from Hugging Face without altering the parameters, weights of these LLMs. For uncertainty estimation, we consider 3 tasks: question answering, multiple choice, and machine translation. The datasets for these tasks consist of pairs of input, x_i, and true output, y_i, text, true, for each sample. We use a few-shot prompting approach with 5 examples for multiple choice tasks and 3 examples for other tasks to enhance the LLM's learning ability and ensure the responses are in the desired format. The tasks involve answering questions based on provided text, COQA, or pre-training knowledge, trivia QA, selecting the correct answer from multiple choices, MMLU dataset, and translating text, WMT 2014 dataset. We evaluate the correctness of the LLM's responses using scoring functions like Rouge 1 and Blue Score. We compare our supervised approach with existing benchmarks that predict sentence generation uncertainty using measures like maximum or average entropy or probability. These benchmarks do not require additional supervised training and can estimate uncertainty effectively. Our approach includes 3 versions: black box supervised, B-flat-S, gray box supervised, G-flat-S, and white box supervised, WBS. These versions differ in the availability of the LLM during training. We train a supervised uncertainty model, HAT-G, based on the random forest model. To evaluate our models, we use the area under the receiver operator characteristic curve, AUROC, metric, which is suitable for uncertainty estimation tasks. For uncertainty calibration tasks, we employ standard calibration metrics and present the results accordingly. Section Summary. In this section, we systematically evaluate our supervised approach for estimating uncertainty in large language models, LLMs, through numerical experiments. We consider tasks like question answering, multiple choice, and machine translation, using open-source LLMs like Llama 2-7b and Gemma 7b. Our approach is compared with state-of-the-art benchmarks, and we implement 3 versions of our supervised approach: black box supervised, B-flat-S, gray box supervised, G-flat-S, and white box supervised, WBS, achieving performance evaluation using the AUROC metric. Section: Performance of Uncertainty Estimation. In this section, we will discuss the performance of uncertainty estimation. We will start by presenting the results for the uncertainty estimation task in question answering and machine translation. These tasks can be seen as natural language generation tasks, so we will present their results together. Our proposed supervised method is compared against existing benchmarks in terms of AUROC in a table. We observed that our methods generally outperform the existing benchmarks, which are mainly unsupervised and rely on a single score. Our supervised method follows a standard pipeline for training an uncertainty estimation model, which contributes to its advantage. Our methods rely on labeled datasets, unlike the unsupervised benchmarks. The experiment results demonstrate the potential of labeled datasets in understanding uncertainty in language models' responses. We found that our method G-flat-S, which uses probability-related features, can significantly improve uncertainty estimation compared to ad hoc methods based on a single score. Additionally, our method WBS, which utilizes hidden activations, shows a clear advantage over G-flat-S. The table also reveals that no single unsupervised method consistently outperforms others across different datasets and tasks. For instance, AVG-ENT performs well for machine translation but poorly for question answering. This inconsistency underscores the limitations of unsupervised approaches in uncertainty estimation for language models. Furthermore, we observed that the performance of B-flat-S is comparable to or even better than WBS. The effectiveness of uncertainty estimation depends on the specific language model used. For example, in the Trivia QA task, BBS performs better than WBS, possibly due to the different knowledge encoded in the language models. Despite some variations in performance, BBS shows promise for estimating uncertainty in closed-source language models. Moving on to the multiple-choice task, our supervised approach demonstrates an advantage over benchmark methods on the MMLU dataset. The results align with our previous findings in the uncertainty estimation task. To gain further insights into uncertainty estimation, we use visualizations to explore how different layers of language models impact the process. Previous studies suggest that middle layers and last layer activations of the last token are crucial for supervised learning. We conducted experiments with different layers and token activations, focusing on natural language generation tasks. The visualization results indicate that middle-layer activation features generally perform better than last-layer features across various tasks and language models. Section Summary. In this section, we evaluate the performance of our uncertainty estimation method on question answering and machine translation tasks, showing that our supervised approach outperforms existing unsupervised benchmarks. We highlight the importance of labeled datasets in improving uncertainty estimation in language models, with our method G-flat-S using probability-related features and WBS utilizing hidden activations, demonstrating varying performance based on the specific language model used. Our findings suggest that incorporating middle-layer activations for uncertainty estimation may yield better results compared to using last-layer activations in language models. Section: Scaling Effect. In this section, we examine whether larger language models, LLMs, with hidden activations impact our method of estimating uncertainty. To compare fairly, we keep the target LLM constant and change the tool LLM for analysis. For instance, in one scenario, we use Gemma 7b to generate outputs and analyze uncertainty using Llama 2 to 7b, Llama 2 to 13b, and Gemma 7b. We observe that there is no significant difference in performance between Llama 2 to 7b and Llama 2 to 13b, or between Gemma 2b and Gemma 7b. This suggests that larger LLMs do not always encode better uncertainty knowledge. We recommend using the same LLM for generating outputs and evaluating uncertainty, based on the performance of WBS. We then analyze the correlations between neuron activations and labels in the histograms. We notice that certain neurons have strong positive or negative correlations with the labels for both LLMs. These neurons indicate uncertainty in the LLM's responses when activated. Gemma 7b has more significant neurons than Llama 2 to 7b, aligning with its better performance. This highlights that LLM's hidden activations contain information about uncertainty in their outputs. By examining specific neurons' activations with high and low correlations, we observe distinct patterns when the response is correct versus incorrect, reflecting uncertainty in the LLM's responses. Next, we differentiate between uncertainty estimation and uncertainty calibration tasks. Improving uncertainty estimation typically leads to better calibration performance. We present calibration results, showing the advantage of our supervised methods over benchmarks, consistent with a UROC performance. We use histogram binning due to limitations with other calibration methods. It's crucial to note the close relationship between uncertainty estimation and calibration tasks, emphasizing the need for additional procedures to extract uncertainty information from LLMs. We also evaluate the transferability of our methods in out-of-distribution settings for question answering and multiple-choice tasks. By training on one group and testing on another, we assess robustness. In question answering tasks, we observe differences between datasets, impacting model performance. Despite slight performance drops in out-of-distribution scenarios, our methods consistently outperform baselines. The hidden layers in LLMs show similar patterns in encoding uncertainty information, enhancing the overall capacity of the uncertainty estimation model. In cases of significant distributional shifts, retraining or recalibrating the model using test data may be beneficial.